All right, let's go over another concept very similar to work energy theorem and its usefulness, because you could solve problems that you would solve with this idea of impulse using Newton's second law in kinematics, but it's much easier to use impulse. It makes it more of a plug-chug, similar to work energy theorem here. Now, impulse is the change in an object's momentum due to a net force being applied to it. So impulse I is the force, net force that you apply, assuming that force is constant, right, times the time that you apply that force. You push with 5 newtons for 3 seconds, so 5 times 3, an impulse of 15 kilogram meters per second. Impulse actually has the same units as momentum because impulse is also equal to the change in momentum. Now, this idea of impulse, many physicists actually don't even like to use the word impulse, so they don't actually include it in their equations because impulse isn't something that you can measure. It's not something you really use. You apply a force over an amount of time. Sometimes, by the way, you'll see this equation F delta T, change in time. Instead, though, impulse is just an in-between, right? If I is equal to ft and I is equal to delta p, well, the equation that really matters is this. Delta p equals ft. Change in momentum equals force times time. And that, just do a quick proof for you on that to show that the two are the same. Delta p, right, change in momentum, ft, well, change in momentum, assuming that we don't change the object's mass, right, and we're not changing its momentum as it moves along by altering its mass, the only thing that's going to change is the velocity. So the velocity is going to grow or shrink delta v. Force is ma, right, mat. Now, we can also say a, right, is delta v divided by t. That's the equation for constant acceleration, right? So delta v over t times my t, and as you can see here, my two t's from the velocity and the time there cancel out, which leaves me with m delta v equals m delta v, just quickly proving that the two are exactly the same there. And then that's not something that's overly important to you. Just wanted to put down the proof really fast. These two are the same, that force times time is the same as your change in momentum. Units, kilograms per meter, kilograms meter per second, also the Newton second, same thing, tomato, tomato. Whenever you break down what the Newton is, it comes out to kilogram meters per second there. The key with this is these equations here do not include displacement. It includes time, but not displacement. Now, work energy theorem included displacement, but not time. So similar to your kinematic equations, where of the 4 kinematics, each one left something out. So does impulse and work energy theorem. So you can pick the one that fits the problem best, that makes it a lot easier to solve with. Let's see, doesn't include displacement, that's the critical factor. Also, similar to work energy theorem, the area under a curve or area under the graph is the impulse, or also it's the change in an object's momentum. So the area under a force time graph is the object's momentum. Here's a quick proof of that. So I have over here a force time graph, 3 newtons, 10 seconds, and it's just flat. So the area underneath, this area right here, is going to be equal to, this is a nice rectangle, your base, which is the time, right, times your height, which is the force. And force times time is the impulse or the change in momentum, delta p. Now, if it was just a nice flat line like this where the force remained constant, you could just plug and chug through your equation, right? You know, through force times time gives me a change of an object's momentum, and that's useful because then I can calculate how much the object sped up or slowed down. But what if the force isn't constant? What if the force changes like over here, that it starts out increasing, you know, you're hitting the gas pedal on a car, right? As you press the gas pedal further down, you're applying more gasoline into the engine, so you're actually applying more force, and then you get to a spot and you level off the amount of force to continue to accelerate at a constant rate instead. Whenever you have this, you can't just plug it into ft, right, because the force is changing here. Instead, you would get the area under the graph, right, do a piecewise here, divide it in half right here, you can get the area of the triangle plus the area of that rectangle to give you the change in momentum. All right, so let me solve a couple of problems for you. First, let's deal with a car engine. And the car engine can provide a maximum force of 3,250 newtons to try to accelerate my just over 700 kilogram car. And I want to know what's the car's best 0 to 60 miles per hour kind of car lingo. That means the car is going from an initial 0 velocity all the way up to 60 miles per hour is 26.8 meters per second. So how fast can it go? In other words, we're going to push the engine as hard as it can. We're going to use every ounce of force to keep our time as low as possible. Now, let me take kind of a step aside and talk about this idea of change in momentum just to make sure we don't mathematically get confused here. Anytime you have change in something, it's the final, so final momentum minus initial momentum. What you ended up at minus what you started out at. That's the change in, or this delta sign here. So if I continue to work that, change in momentum is mass times velocity, so mass times final velocity, right? Final here, final there, minus your mass times your initial velocity. The mass of the object, since it's only one object, it's not a collision, only one object. The mass of the object isn't changing, right? So I can factor the mass out. What's changing is the velocity. It's speeding up or slowing down. So I can have final minus initial, and final minus initial velocity is the same as delta V. So you're going to see us change delta P, or change momentum, into M delta V all the time. Just know delta V, you take the final velocity minus the initial. Just wanted to make sure we didn't get confused on that. So it doesn't tell me anything about time in this problem. So this lends itself, or excuse me, it's asking for time. It doesn't tell me anything about displacement in this problem. So this lends itself perfectly to impulse. Now I could solve this using Newton's second law, F equals ma. I know an F, I know an m, that'll let me get an a, right? Then I know a final velocity and an initial velocity, that'll let me get a time. That's a multi-stepper. Or I could just go ahead and plug straight into impulse. Impulse is delta P equals Ft, right? So that's m delta V equals Ft. And now I know everything. I can just actually substitute in and solve out. No multiple steps. Final velocity, 26.8, minus my initial, 0, equals the maximum force that I'm using, 3,250, times how long I have to exert that force to get up to my 26.8 meters per second. And whenever I substitute in and solve all the way down, I get a 0 to 60 time of 6.04 meters per second. Three significant figures. Notice 3 here, 3 here, 3 here. And I'm not using the 60 anywhere in there with only one sig fig, so 3 sig figs everywhere. This is actually a pretty fast car. Right, let me talk about really fast how to recognize these impulse problems. If you see a problem where we're talking about applying some force, whether, like here, a place kicker's foot, kicking a football, it's applying a force to it. So you see something about a force being applied for an amount of time, here's 87 milliseconds, right? And then you're not seeing anything about acceleration, but you are seeing things about velocities, right? So if you see force, times, and velocities, you're looking for the force, you know a time, and you know two velocities, final and initial. Or you know your final initial velocities and your force, and you need to know time. Those things scream use impulse, use impulse. You can go back to Newton's second law in kinematics. It's just not as sleek. It's going to take you an extra step or two, which isn't necessarily a bad thing. Another thing that I want to mention is you can have a negative change in momentum, right? If the force here is being applied to, let's say, stop you, decelerate you, as opposed to accelerate you, so you would end up with a negative force over here, you can have a negative change in momentum where your final velocity, let's say you're trying to come to a stop, your final velocity is 0 and your initial velocity was some high number. In this problem, though, we are trying to accelerate a football. Place kicker's foot kicks a football and is in contact with this 41 kilogram football for 87 milliseconds. I'm going to start using now, whenever I see milli, I'm slapping on a times 10 to the negative 3, and I'm just going to let the calculator work it out from there. I don't have to spend any extra mental energy. Milli means times 10 to the negative 3. Accelerates the ball up to 23 meters per second in an attempt to make a 45-yard field goal. That is extraneous. We don't even need to know about that. What is the average force that his foot exerts on the ball? So once again, I'm looking for force. I know a time. I know a change in velocity. This screams, let's use impulse here. So momentum is m delta v Ft here, right? And so now I just need to substitute in what I have. I know the mass is 0.41. My change in velocity, I'm going up to a final, so 23, minus my initial. The football was initially at rest, sitting there on the tee if you're familiar with football, equals F, what I'm looking for, the average force, because technically the force is going to change as the kicker's foot continues to go into the ball and then the ball begins to bounce off of his foot. But the average force that we're looking for here, F times T, and I'm going to use scientific notation, so I don't even have to worry about jumping the decimal, 87 times 10 to the negative third. Now once again, this is, and remember I taught you this at the beginning of the year, this is technically not correct scientific notation, but your calculator does not care. Whenever you change milli, prefix milli, means times 10 to the negative 3. You just put it on and it's going to work out. Now it's just algebra to plug into a calculator. And so my average force comes out to be, using significant figures, 110 newtons is how much force he was actually exerting on the ball there on average. And then I just want to go ahead and put in solving this around just using variables to where you get F by itself first, then you can plug all of that into the calculator at the exact same time. That way you don't have any rounding mistakes. So better if you can work that way.